right? Okay, so this is the end of the series of 2D, 3D, and then we've been looking at criterias. Okay, so the next topic, so this is a new topic that I'm going to teach. Okay, so the next topic that I'm going to teach is something that you guys are familiar with, and I'm going to add on something new. Okay, so this is the design. Oops, wrong color or wrong pen. Design of beams using the integration method. Okay, and the integration method over here is very simple integration. Okay, nothing complex. So now, if we have a structure, okay, let me, right? So the integration method over here, we are going to identify, find the shear force and bending moment equations. Okay, so it's not just, I know all of you know how to sketch the shear force and bending moment diagram or diagram. I have no dispute. But now we want to identify the equations. Why? Because later on, okay, next week, we're going to find the deflection, which I have not learned yet before. Okay, so we're going to use the integration method, and I'm going to tell you the power of the integration method. So now, if we have a structure now that's simply supported, okay, now we have a structure that's simply supported. Okay, so this is our structure now, right? So you have a point over here, right? And this is your point A, and over here is our point B, right? Now our structure is no more uniform distributed, or is no more gradient distributed anymore. Now our structure has a distribution that look like this. Okay, so this is the sort of distribution that we have. Okay, then we have our load. So it's all so this is the omega as a function. So this is the function of the distributed load. Okay. So now we are now going to have a relationship now, okay, where we have dv over dx is equal to minus omega as a function of x, where omega as a function of x is the function of the distributed load. Okay, so this is neither evenly distributed load nor a gradient distributed load, right? So from here, we want to find the shear force and bending moment equation for 2 points. Okay, so this is my point C over here. Next one over here, this is my point D. So the datum will be always on the left hand side of the structure. So that's our datum, right? So if that's our datum, the distance from here to here this is x, c, and the distance from here to here this is x, d. So the first relationship I've written down, right? So the first relationship is dv over dx is equal to minus omega x, okay, where omega x is the is the uh, is the equation of the distributed load. Okay, so between point C to point D, right? Between point C to point D, right? So the shear force, you integrate dV, right? And this is between point C, V of C, and V at point D. This will be equal to the distance xc, xd, right? And it will be equal to minus omega x dx. Okay. So from here, you will have V at point D, the shear force at point D, minus the shear force at point C is equal to the integral of xc to xd minus omega as a function of x dx. And this expression over here, okay, we can relate to bending moment. Okay, so if we have the deviation of dm over dx, this is equal to v as a function of x. Okay, so from here, we know that this is also equal to what? This can be also be equal to dm over dx. Okay, so again, between C to D, right? So we're going to have moment at point D minus by the moment at point C. This will be equal to xd, xc to xd will be equal to v as a function of x dx. Okay, so I probably you guys have seen this in your math before. Okay, now can anyone tell me why is it beside later on you have to learn how to do deflection of the beam, calculate the deflection. Why is it so important to of this method? Anyone? Why this method is so critical? Anyone? Or so versatile? Can anyone think of any advantages yet?
If you know the loading, you can just integrate, and get a lot more information than with the other methods quicker.
Say it again.
If you know the loading conditions of the beam, then you can use the integration method to get more information about like the bending moment and the shear force much easier than you may be able to do it with the other methods.
Yeah, partly right. Okay, so now, yeah, partly right. Okay, so let's look at evenly distributed load or gradient distributed load. Okay, so if we have when you guys learn this, you guys learn it based on positive shear and positive bending moment, right? So if we have an evenly distributed load, okay, this is your point A, and this is your point B, and you have an evenly distributed load, which is omega, and this is L, right? When we consider the free body diagram, this is straightforward, right? We know that, so this is AY, this is BY, and the equivalent load. So the equivalent load is equal to omega multiplied by L, right? And the distance from here to here is L over 2. Straightforward, right? So this is what we call a condition of evenly distributed load. Okay. Now, if now we have a gradient distributed load, it's also easy, right? So we have point A. We have point B. So now our load is no more a flat line. Okay, it has a gradient, right? It has a gradient. So this is omega naught. Okay, the distance from here to here is L, right? So the equivalent load is also straightforward. Okay, all the equivalent load is area under the curve. So straightforward, right? So this is our AY and this is our BY, right? And then our equivalent load is more biased towards the right hand side. So this is our equivalent load. Right, so equivalent load is the area under the triangle, so multiplied by omega naught L, right? And then the distance from here to here, the position of the equivalent load is L over 3. So this is a gradient distributed load, right? Okay, so both of them, we can identify the position of the equivalent load easily, yes or no, right? So now, this is what we have learned, or what we have learned in 2PO4. Very straightforward. In 2PO4, it's either a flat line or gradient line or a combination of both, right? Sometimes it can be a trapeze, okay? Now, can someone tell me what's the problem with this now? The equivalent load is easy, right? The equivalent load is easy to find. All you need to do is integrate within a certain limits omega as a function of x dx. That is your equivalent load. What is the problem? Anyone? What is difficult to find? The position of, yeah, the position. Okay, what is difficult to identify is the position of the equivalent load. Right? Where is it acting on? So if you have found, so I'm going to use a different. So if this is your equivalent load, right? So this is your equivalent load. What is this distance? Right? I don't know. You cannot just make a guess. Okay? So this is the power of the integration method. However, to use the integration method, okay, we're going to do integration, yes or no? You have to know your boundary condition or the boundary condition. So I'm going to do I'm going to do an example now. Okay, I'm going to do an example now. Okay, so the example that I'm going to do, so this is example number 2. Okay, the structure is still not very complex, loaded. Okay, so we will have a cantilever beam. Okay, so it's been built in. So this is our cantilever beam. This is our point A, and this is our point B. And then on our cantilever beam, we have a load distribution that looks like this. Okay, and then we have our distance. So our distance over here is 6 meters. Okay, so what we want to find is we want to find the shear force